Labor shift scheduling looks simple at first. Just put people on a calendar. But in real operations, it is one of the most constraint-heavy decisions you can make. The core goal is to assign employees to shifts, so the operation is fully covered, skills are present where needed, and labor rules are respected, all while controlling cost. If you get it wrong, the failure mode is immediate. Customers wait, service levels drop, overtime spikes, and burnout rises. This problem appears everywhere: call centers, hospitals, retail, hospitality, and manufacturing. What makes it hard is not one single constraint, but the fact that coverage, cost, skills, rest rules, and fairness all interact across time. A schedule that looks cheap on paper can be operationally unsafe, legally non-compliant, or simply unacceptable to the workforce. Our scenario is Global Tech Solutions, a multinational technology company running a customer support call center that must be staffed 24 hours a day, 7 days a week. The workforce includes 45 customer service representatives, and they are not interchangeable. They have different skill levels, language capabilities, and availability constraints. The day is divided into 3 8-hour shifts. The morning shift runs from 6 a.m. to 2 p.m. The afternoon shift runs from 2 p.m. to 10 p.m. The night shift runs from 10 p.m. to 6 a.m. Right away, this structure creates operational pressure. Night shifts are harder to staff, handoffs between shifts must be clean, and coverage must follow real demand patterns rather than a static headcount rule. In this call center, the scheduler is balancing multiple objectives at the same time. First, you must meet coverage during the peak demand periods, so the operation does not fall behind. Second, you want to minimize labor costs because staffing is a major expense. Third, you want to respect employee preferences when possible, because preference violations show up later as absenteeism, turnover, and morale problems. On top of that, you have hard constraints you cannot ignore. You must maintain skill diversity across shifts, meaning the schedule needs the right mix of languages and capabilities at every time window. You must comply with labor regulations such as maximum consecutive working days and minimum rest periods. And you must distribute weekend and holiday work fairly because perceived unfairness is one of the fastest ways to destabilize the workforce. We will approach the same scheduling problem through a tiered toolkit, moving from exact modeling to practical decision support. Tier 1 builds a complete integer programming formulation, which is the clearest way to state what the problem is and what feasible means. Tier 2 introduces a classic heuristic, a priority-based greedy method, which trades optimality for speed and simplicity. Tier 3 uses a genetic algorithm, a metaheuristic that searches globally by evolving candidate schedules over generations. Tier 4 reframes scheduling as sequential decision-making and uses reinforcement learning to learn an assignment policy from feedback. Tier 5 embeds scheduling inside an integrated digital twin, so the schedule becomes part of a living system with forecasting, monitoring, and continuous adaptation. Later tiers, like Tier 7 and Tier 8, focus on human collaboration and ethics because a good schedule must be both operationally effective and socially acceptable. Tier 1 expresses the labor shift scheduling problem as an integer programming model. Operationally, the decision is straightforward. For each employee, for each day, decide which shift they work, if any. The objective is also clear: minimize the total cost of assignments across the planning horizon. The value of Tier 1 is completeness. You explicitly define the objects you schedule, the inputs you must respect, the decision variable that represents assignment, and the constraints that protect the operation from real failure modes. When this tier is correct, it becomes a benchmark. Even if you do not solve it exactly for large instances, it tells you what the schedule must achieve and what trade-offs you are making. This slide defines the bookkeeping of the model, what entities exist, and how we index them. We define the set of employees, the set of shift types, the set of days in the planning horizon, the set of time periods within each day, and the set of skill categories. These sets are the language of the model. Operationally, sets and indices prevent ambiguity. Coverage is not a vague concept anymore. It is coverage for each time period. Skills are not assumed. They are represented as categories that can be counted. When you later write constraints, every term has a physical meaning. Employees are assigned as shifts on days, shifts cover time periods, and employees contribute skills to the periods they cover. Parameters are the inputs that describe the instance you are scheduling. Demand tells you how many employees are needed in each time period. Assignment cost tells you what it costs to assign a specific employee to a specific shift on a specific day. A coverage indicator tells you which time periods each shift covers, which is how the model links shift assignment to hourly coverage. You also parameterize skills and rules. Skill indicators tell you which employees have which skills. Skill requirements tell you the minimum number of employees with each skill needed in each time period. Availability tells you whether an employee can work a given shift on a given day, and you include labor rule parameters like the maximum consecutive working days allowed and the minimum rest periods between shifts. Operationally, these parameters are where policy meets reality. They are the difference between a theoretical schedule and one that can actually be staffed. The decision variable represents the single core action, assigning an employee to a shift on a day. It is a yes or no choice. Either the employee is assigned to that shift on that day, or they are not. Operationally, this variable is the lever the scheduler controls. Everything else in the model, cost, coverage, skills, feasibility, flows from these assignment decisions. Once you have a clean decision variable, you can reason clearly about constraints like one shift per day or cannot assign someone when unavailable, because those rules become simple statements about allowable assignment patterns. The objective function minimizes total assignment cost. It adds up the cost of every employee shift day assignment that the schedule chooses. Operationally, this objective forces discipline. It prevents overstaffing when demand does not require it, and it makes trade-offs explicit. But it also highlights a key caution. Cost is not the only thing the business values. If you minimize cost without strong constraints for coverage, skills, rest, and fairness, you will produce a schedule that looks cheap but fails in execution. That is why the objective must be paired with complete constraints that represent service and policy requirements. This constraint ensures there are enough employees covering each time period, on each day, to meet demand. It works by counting the employees assigned to shifts that cover that period, and enforcing that the count is at least the demand requirement. Operationally, demand coverage is the fundamental service level protection. Without it, the model could assign too few people to save cost, and the schedule would immediately fail as customers queue and wait times explode. This constraint prevents the most visible failure mode in staffing, undercoverage during the hours when demand is high. This constraint ensures that staffing is not only sufficient in quantity, but also sufficient in capability. It counts within each time period how many assigned employees carry each required skill, and enforces that the count meets the minimum requirement for that skill. Operationally, this is what stops you from staffing a shift with enough people who cannot actually handle the workload. In a call center, that could mean not having enough language coverage, not having enough technical support capability, or not having enough people trained for specific customer segments. Skill constraints protect quality, not just volume. Availability is the feasibility filter that connects scheduling to real human constraints. This constraint prevents assigning an employee to a shift on a day when they are not available for that shift. Operationally, availability captures vacations, training, part-time rules, contracted hours, or personal constraints that the organization has accepted. If you violate availability, the schedule is not merely suboptimal, it is unstaffable. This constraint prevents paper schedules that collapse the moment the week starts. This constraint enforces that each employee works at most one shift per day. It sums all possible shift assignments for an employee on a day and requires that the total is no more than one. Operationally, this protects against unrealistic plans that overload individuals. Even if you could pay overtime, stacking multiple 8-hour shifts in a day is typically impossible or illegal. This constraint keeps the schedule within basic human and regulatory limits, and it also simplifies handoffs and fatigue management. This constraint limits how many consecutive days an employee can work. It looks at windows of days and ensures the schedule does not assign work on too many days in a row beyond the allowed maximum. Operationally, this is a fatigue and compliance constraint. The risk it prevents is hidden but severe. When people work too many consecutive days, errors rise, sick leave increases, and turnover accelerates. In a 24-hour operation, Violating consecutive day limits can also lead to a staffing spiral where the schedule becomes harder and harder to fill as the workforce burns out. This diagram visualizes the structure of the scheduling problem. Employees on one side, days and shifts on the other, and a grid of assignments constrained by coverage, skills, and labor rules. Use it as a map of how decisions and constraints connect. Operationally, the diagram helps you see why scheduling is not just a list of names. Each assignment simultaneously affects coverage by time period, skill mix, individual workload, and downstream fairness. When a schedule feels fragile, it is usually because the grid is tight. Small changes ripple through multiple constraints, which is why structured models and systematic algorithms matter. To make the model tangible, consider a simplified example with 3 employees across 2 days and 2 shift types, morning and afternoon. Demand is 2 employees per shift. Morning shifts cost $100 per employee, and afternoon shifts cost $120 per employee. The reported optimal outcome is a total cost of $720. The purpose of this example is not realism in scale, but clarity in mechanics. With a small instance, you can trace exactly how coverage and cost trade off, and you can verify that the model produces a schedule that meets demand at minimum cost. Here's the specific schedule from the example. On Monday, employee 1 works morning, employee 2 works morning, and employee 3 works afternoon. On Tuesday, employee 1 works afternoon, employee 2 works afternoon, and employee 3 works morning. Operationally, you should read this as a feasibility check. Every shift meets the demand requirement, no one is assigned twice in the same day, and the pattern distributes work in a simple, balanced way across the 2 days. The key takeaway is that the model does not just give a number, it gives an executable assignment plan that achieves minimum cost under the stated rules. Tier 2 uses a priority-based greedy algorithm. Instead of solving the full integer model exactly, it constructs a schedule step by step, assigning employees to shifts based on a ranking rule. The ranking can combine availability, skill match to current requirements, cost efficiency, and workload balance. Operationally, the advantage is speed. You can run this approach quickly for large teams and long horizons. The risk is myopia. A greedy choice that looks good for the current shift can create a shortage later, especially for scarce skills or difficult-to-staff shifts like nights and weekends. The heuristic must be designed so it does not spend critical resources too early. This flow shows the loop. Consider the current day and shift, compute priorities for available employees, select the best candidates, check feasibility with respect to constraints, assign employees until demand is satisfied, and then move forward. Operationally, this is the real-time scheduler's workflow. The algorithm is not just sorting once. It must recompute priorities as assignments change workloads and as remaining demand evolves. When the loop is designed well, it produces schedules that are consistent, explainable, and fast enough to update when absences or demand changes occur. In this first pseudocode segment, focus on how the algorithm initializes the problem, reading the planning horizon, preparing employee availability and skill data, and setting up the demand requirements per day and shift or per time period. Operationally, the critical design choice here is what the algorithm knows at the moment of assignment. If the data structures track remaining demand and required skill counts explicitly, the heuristic can make decisions that protect future feasibility. If not, it will tend to overfit to cost and availability and underperform on skill coverage. This segment typically contains the priority scoring logic. It defines how to compute a score for each eligible employee based on factors like availability, skill match to current requirements, cost of assignment, and how many shifts the employee has already been assigned. This part usually covers the assignment loop and the update steps. Once an employee is assigned, the algorithm updates remaining demand, updates remaining skill requirements, and updates the employee's workload counters. It then repeats until the shift is filled, or no feasible assignment remains. This example output corresponds to a 7-employee, 5-day call center with morning, afternoon, and night shifts. The output is a concrete schedule produced by the greedy policy. Operationally, you use this kind of output to audit feasibility and fairness. You check that each day's shifts meet coverage, that required skills appear where needed, that the same person is not repeatedly assigned to unpopular shifts, and that the schedule does not silently violate rest or consecutive day limits. Example outputs are not decoration. They are a quality gate for whether the heuristic is producing operationally viable schedules. This slide continues the example schedule, likely showing a chunk of days, shifts, and assigned employees. As you read it, focus on whether the structure matches the demand pattern and whether the same names appear too frequently in the most difficult shifts. Operationally, a common failure mode is greedy overuse. If the heuristic always picks the cheapest or most skilled person, that person becomes overloaded. The right way to read the table is to ask, does the algorithm distribute workload while still meeting skill needs? Or is it solving today by borrowing too much from tomorrow? This section usually shows the next portion of the schedule. Look for continuity. Does the schedule create reasonable patterns, or does it produce chaotic assignments that change dramatically day to day? Operationally, stability matters. Even if two schedules have the same cost, the more stable one is often better because it reduces confusion, reduces last-minute changes, and improves employee satisfaction. A strong heuristic tends to produce patterns that look like something a human scheduler would accept, not just a mathematically feasible grid. This final part of the heuristic output should complete the example week. Use it to check end-of-horizon effects, where greedy algorithms sometimes fail by pushing problems to the end, such as leaving the hardest-to-staff shifts for last. Tier 3 treats the entire schedule as a candidate solution that can be improved through evolutionary search. In a genetic algorithm, each candidate schedule is a chromosome, and the algorithm maintains a population of such schedules. Operationally, the key change is that you are no longer committing to one greedy construction path. You explore many alternatives, evaluate them, and recombine the best features. This is valuable when the search space is huge and the constraints interact strongly. Exactly the situation in workforce scheduling with skills, rest rules, and fairness requirements. This slide illustrates the evolution cycle. Start with an initial population of schedules, evaluate their quality, select the better ones, create new schedules through crossover, introduce variation through mutation, and repeat over generations. Operationally, this cycle provides a controlled way to search globally. Selection pushes the population toward better schedules. Crossover transfers useful patterns, such as strong weekend balancing or robust night coverage. Mutation prevents the algorithm from getting stuck by introducing new combinations. Over time, you expect the best schedule in the population to improve steadily, not by accident, but by systematic exploration. The fitness function is how the genetic algorithm decides what better means. In this problem, the fitness balances cost, coverage quality, and penalties for constraint violations. In other words, the algorithm tries to reduce cost while also avoiding undercoverage and avoiding illegal schedules. This pseudocode typically covers chromosome representation and initialization. The algorithm must encode a full, multi-day, multi-shift assignment in a way that crossover and mutation can modify without destroying meaning. This segment usually describes evaluation, computing total cost, checking coverage and skill satisfaction, and computing violation penalties. It also defines selection, such as tournament selection or ranking-based selection. This segment often covers crossover and mutation operators. Crossover combines two parent schedules to produce offspring. Mutation randomly tweaks assignments to explore new patterns. This part typically includes the main generation loop, elitism, and stopping criteria. Elitism preserves the best schedules, so progress is not lost. The loop repeats for a fixed number of generations or until improvement stalls. This slide shows example results from the genetic algorithm run, typically a schedule snapshot or performance metrics. Focus on what improved relative to the heuristic: lower cost, better coverage consistency, fewer violations, or better workload balance. This continuation often shows additional results, such as another part of the schedule or a second metric view. Look for fairness and stability improvements, not just cost. Tier 4 reframes scheduling as sequential decision-making. Instead of producing one schedule in one shot, an agent makes assignments step by step, observing the current situation and choosing the next action. In this formulation, the state includes the current day and time period which employees are available, the skill distribution across already staffed shifts, remaining demand requirements, and historical assignment patterns. It may also include fatigue and preference indicators. Actions can include assigning a specific employee to the current shift, requesting overtime, swapping assignments, or leaving a position unfilled with a penalty. Operationally, this matches how scheduling often happens in reality, as a sequence of decisions under constraints and uncertainty. The reward function defines what the agent learns to optimize. It includes a direct cost term for assignments, penalties for understaffing, penalties for rule violations, and a positive term for employee satisfaction when preferences are respected. Operationally, reward design is where you encode the business truth. If understaffing penalties are too low, the agent will learn to save cost by leaving shifts short. If satisfaction rewards are too high without guardrails, it may overfit to preferences and fail coverage. The reward must reflect real priorities. Meet coverage and compliance first, then optimize cost and satisfaction within those boundaries. This slide shows the learning loop. The agent observes a state, chooses an action, the environment updates the schedule and constraints, and returns a reward. Over repeated episodes, the agent learns which sequences of assignments lead to high long-term reward. Operationally, the key idea is adaptation. In dynamic environments, like call centers where demand fluctuates and availability changes, learning-based methods can adjust better than static rules. But this only works if the environment model is realistic and if infeasible actions are handled properly, either by removing them from the action set or applying strong penalties when the agent attempts them. This pseudocode segment typically defines the deep queue network structure and how states and actions are represented. The model estimates the value of taking each action in the current state. Operationally, state representation is the foundation. If the state does not include remaining demand or skill requirements, the agent cannot learn to satisfy them. If it ignores fatigue or recent assignments, it cannot learn fairness patterns. Good reinforcement learning performance depends as much on the state and action design as on the learning algorithm itself. This segment often describes action selection, including exploration versus exploitation. Early in training, the agent explores to learn. Later, it exploits what it has learned to choose better actions consistently. Operationally, exploration must be safe. In a real scheduling system, you do not want exploration to generate illegal schedules. That is why during learning, infeasible actions should be masked out or heavily penalized. Even in simulation, allowing too many illegal moves wastes training time and teaches the agent the wrong structure of the problem. This part usually covers experience storage and sampling, such as a replay buffer. The agent stores state action reward transitions and learns from sampled batches. Operationally, replay improves learning efficiency and stability. It reduces the risk of the model forgetting good patterns and helps it learn from rare but important events like tight staffing on night shifts or hard skill bottlenecks. In workforce scheduling, those edge cases are often where the real value is. This segment typically covers the training update step, computing a target value and adjusting the network parameters to reduce prediction error. Operationally, this is where learning becomes real improvement. If the training signal is noisy because rewards are poorly scaled or because the environment is inconsistent, training will be unstable and policy quality will fluctuate. A practical approach monitors training curves and validates policies on held-out scenarios to ensure the agent is not just memorizing one pattern. This part often introduces stabilization techniques, such as a target network that updates more slowly than the main network. Operationally, stabilization matters because scheduling is a long horizon problem. Decisions now affect feasibility days later through consecutive day rules and fairness. Without stabilization, learning can chase short-term reward spikes and become brittle. With stabilization, the agent can learn smoother policies that generalize across different demand patterns and availability structures. This segment usually covers training loops across episodes, evaluation checkpoints, and how the policy is extracted for use. Operationally, you want clear evaluation criteria. Does the agent meet demand? Does it maintain skill coverage? Does it reduce violation rates? Does it keep overtime controlled? The best practice is to evaluate against multiple scenarios, including stress cases like high demand peaks and low availability weekends, because that is where scheduling systems succeed or fail. This slide presents example results from training the reinforcement learning approach on a larger facility, described as a complex 20-employee setting. The key idea is that training produces a policy, not just a one-time schedule. Operationally, results should be interpreted as policy behavior. Does the agent learn to allocate scarce skills early, protect rest rules, and avoid undercoverage? A good reinforcement learning outcome is not only a lower-cost schedule, but also fewer coverage gaps and fewer compliance issues, achieved consistently across episodes rather than in one lucky run. Tier 5 moves from algorithmic scheduling to system scheduling. A digital twin connects scheduling decisions to real-time data streams, forecasting, constraint monitoring, and continuous adjustment. Operationally, the digital twin perspective recognizes that demand changes, people call in sick, training needs appear, and policies evolve. Rather than producing a static weekly schedule, the system continuously monitors key signals, predicts upcoming needs, and re-optimizes within guardrails. This is especially powerful in 24-hour operations where the cost of stale schedules is high. This slide describes the digital twin architecture as multiple interconnected subsystems. It includes workforce simulation components that model fatigue and performance, demand forecasting engines, constraint management systems for compliance, and analytics modules that track operational key performance indicators. Operationally, architecture matters because it defines responsiveness. If forecasting is isolated from scheduling, the schedule reacts late. If compliance monitoring is not integrated, you only discover violations after they happen. A well-designed system uses clear interfaces and event-driven updates, so scheduling decisions can respond in time to prevent service breakdowns. This example describes Medcare Regional Hospital implementing a digital twin for nurse scheduling across 12 departments. The reported outcomes include a 23% reduction in overtime costs and a 34% improvement in schedule stability, meaning fewer last-minute changes. It also reports a 91% nurse satisfaction rate with schedule fairness and a 15% reduction in patient readmission rates correlated with improved staffing. Operationally, these metrics show why digital twins matter. They link scheduling quality to both cost and care outcomes. Stability and fairness are not soft goals. They show up in retention, performance, and patient outcomes. Tier 7 focuses on collaboration, a human plus artificial intelligence partnership, sometimes called a centaur model. The idea is that artificial intelligence can process huge constraint sets consistently and propose strong schedules while humans contribute contextual judgment, relationship management, and ethical oversight. Operationally, this avoids a common failure mode, fully automated schedules that are technically feasible but socially unworkable. Human schedulers often know special circumstances, team dynamics, training trajectories, and local policies that are not captured in formal inputs. The best systems let artificial intelligence draft and optimize while humans review, adjust, and approve with full visibility into trade-offs. This slide emphasizes explainable recommendations. The system should be able to say why it suggested a given assignment, using human language tied to skills, preferences, workload, and constraints. Operationally, explainability is adoption. If a manager cannot understand why the system assigned someone to a night shift, they will not trust it. If employees cannot understand why they received a weekend assignment, they will perceive unfairness. A strong partnership system provides explanations, shows alternatives, and gives real-time feedback when a human override causes a constraint violation or a cost increase.